Well, thank you all for being here. It's enjoyable to be here. I was thinking that it was going to be warmer in the morning, but it's cool in the morning. I know you're all used to colder weather, but it's been relatively warm all across the country, at least in the part of the country that I've been in the eastern part. Now, you think that I'm a Southerner, right? But I don't really talk like a Southerner, do I? I've been living in the South more years than I've lived in the North, and I'm not sure exactly where we should demarcate the line. But I've lived in Georgia and North Carolina for more than 28 years, and I've went to school at Texas A&M. So I'm also down. I've been down in hell, so it's been a place. But I have to say that I'm actually more of a Northerner than maybe some of you realize. I worked at the Beaver Lodge Agricultural Research Center in Beaver Lodge, Alberta. That was at the time the most northerly agricultural research station in the world. Now Russia had one earlier that was closed down, and and then they closed down the Beaver Lodge research station too. So it's no longer the most northerly. Anyway, so I've got a few experiences for you that I want to share. The theme that I'm going to share with you is really focused about the biologically active portion of organic matter, and then how we can actually quantify what you have done in the past as far as organic matter accumulation. You can take a soil sample, have it sent off, and analyzed for organic matter. When we analyze organic matter, it's typically we're measuring carbon in the soil, because 58% of organic matter is carbon. And so that would be the actual true measure of organic matter. So whenever I show you graphics of carbon, it's really, you have to think about carbon or as organic matter. And that's the point that I'm trying to make here, is that organic matter is important, it can be important, but there are old parts of organic matter that just simply sit around for a long time and don't do anything. Now I say don't do anything. They're not biologically active, but they also contribute to the physical structure of the soil, and that's important. So I've got a few slides, and I'm going to try to get through them in the amount of time before our break. All right, so I've titled the presentation about managing for the next generation, because really building soil is a long process. It doesn't just happen like if you implement no-till this year and then you try it out and say, well, it wasn't worth it, you probably didn't do any good for yourself, because no-tillage for 1 year is just simply reducing the fuel passes over the field. That's all you're saving there. And so you can actually be more resource efficient with a no-tillage operation, but it doesn't mean that it's going to have long-term impacts on the soil. All right, soil fertility has often been characterized simply by sending a sample and getting an analysis of the chemical attributes of soil. And so soil fertility was reviewed in this paper here by my colleague Josh McGrath down in Kentucky and John Spargo in Pennsylvania. Okay, what are the key elements of soil fertility? Well, we don't often think about it, but carbon, hydrogen, and oxygen are very important elements in the soil, and they're actually part of the soil fertility, and that's because they're participating in organic matter formation. The primary elements that we think of are the nitrogen, phosphorus, and potassium. The nitrogen, phosphorus, and potassium, NPK, those are the elements that you'll get back on a soil test result. But I don't know exactly how it's done in Michigan, but in most state labs, nitrogen is simply, the recommendation for nitrogen is simply that we go to a book value and tell you how much nitrogen to apply. Most state labs don't actually analyze the soil itself for the nitrogen. They'll analyze the soil for phosphorus and potassium, but they don't typically analyze the soil for nitrogen, partly because the nitrogen that a plant takes up is in an inorganic form. It's in nitrate and ammonium, and that nitrate and ammonium is a very small part of the soil nitrogen, and it's very highly variable. If you take the sample today and then it rains 3 inches until you take a sample the next month, then the nitrogen in the soil will be very different. It depends on what the temperature will be. So the NPK is an important aspect, and then we have a whole list of micronutrients, and they all can be important. If they're lacking, we might need strategies to actually increase them. They can be also toxic. They can be too much in the soil. And so that's a good thing that we have soil test analysis in the chemical arena. It's important. And then there are some other elements that may be important as well. All right, so there are some additional considerations to this whole paradigm of testing only for chemical attributes. So there may be other elements that are taken up by plants, and so we don't necessarily want to focus on any one element. There can be toxic accumulation that can interfere with metabolic functions. And soil fertility management provides essential elements in sufficient quantities for successful completion of plant metabolic processes and reproductive activities. Optimum soil fertility requires adequate quantities of elements in a form and location available for plant uptake, meaning that if the element is present in the soil, it may be present in the top 4 inches, if that's the sampling domain, but it may be that but there may be little of it below 4 inches. Or there may be a high amount below 4 inches. And typically we're only testing the soil. Perhaps in Michigan you're sampling to 6 inches, and that's certainly fine. But when we have no tillage and pasture systems, oftentimes, at least in the southeastern US, we're only recommending sample top 4 inches. Irrespective of that, you can sample soil deeper than 6 inches. The plant roots actually go deeper than 6 inches, and we hope that they do. And the idea here is that the elements have to be in the place where the roots need to have them. All right. So there are some other things. Prior to industrialization, agricultural production relied on recycling of organic residues, such as manure and plant residues. We don't have that situation anymore. You know, it's been at least 75 years since we've changed agriculture. And the last 75 years have been a dramatic change, but the most change in agriculture than any other time in history. And we're talking about thousands of years of agricultural history. And it's been in the last 75 years that we've seen so much great change. And many of you would say, well, it's a good thing. And it is a good thing. Don't get me wrong. It is a good thing. But we've bypassed natural limits. There are certain things that we could be doing differently that if we just pay attention to the organic cycling, we might actually make our operations more efficient. Right now, we basically, like for the nitrogen example, we just basically tell you on a recommendation that, well, you just need to have enough. And in the past, since the 1960s, when fertilizer nitrogen became abundant, it was actually just relatively very cheap. You had no concerns. You could just apply as much as you wanted. One of the key things that a USDA scientist back in the 1970s did was develop a system where he related the amount of nitrogen for a corn crop to the amount of bushels that you could produce. And it became very prevalent that we would understand 1 pound of nitrogen per bushel of grain that you wanted to produce. That was a way just simply to reduce the amount of nitrogen that was being applied to some of our lands. And of course, sometimes now we've modified that to 1.2 pounds of nitrogen per bushel of grain. And I'm going to give you some examples of where I think that has failed us. But basically, the industrialization of agriculture really developed when we developed the possibility to develop nitrogen fertilizers, inorganic fertilizers, through the Haber-Bosch process. And that was very important, and that created this condition where global cereal production was on the rise from 1960 to the turn of the century. It was a very large increase. This is global cereal production. And it followed also with high level of nitrogen application, the nitrogen input, the water input through irrigation, and the phosphorus application. So these are just simple summarization of the elements where we see that global cereal production might be considered, well, it has to have these nitrogen, phosphorus, and water inputs. And in some ways it does, but they are just simple associations. That doesn't mean there's a cause and effect. There is likely some cause and effect in there, but we simply all of a sudden start thinking that we need to apply nitrogen fertilizer, phosphorus fertilizer, because we want high yields. But it's not actually mathematically and guided by nature's laws. And so we need to actually understand how nitrogen and phosphorus are made available in the plant. So nitrogen is the most limiting nutrient to plant growth, at least across many different ecological conditions, different environments throughout the world. If we apply nitrogen, we typically get a yield response. And if we don't have nitrogen, we don't get much of a yield
production. And that's important to understand, is that nitrogen is needed, and we need to understand what is the available nitrogen. So I've got an axis here of available nitrogen. Now you might think that, well, you could just equate that with fertilizer input, and you could, but available nitrogen is much broader than just fertilizer input. Remember, 75 years ago, prior to 75 years ago, we didn't have inorganic fertilizers on a regular basis. And so people actually produced food. Now, of course, the food production was lower back then. Don't get me wrong. All of the advancements that we've had are really important. Genetics, the technologies that are in there. But there was no possibility, if we follow that it's only fertilizer input, that we would have not had the food that we did. So nitrogen is important, and this curve is important to understand too. When we add a little bit of nitrogen, we get a large yield response. Because if our soil is completely devoid of nitrogen, we need to have some nitrogen simply to get the plant to be able to produce leaves so that it can be reproductive and produce a food-producing crop. So that's important. But then at some point, it starts leveling off, and it tapers into this optimization there, where we add more nitrogen and simply nothing happens. And that's an important aspect to understand. That's kind of the nature. Well, nitrogen is the most limiting nutrient of plant growth. But if we turn the page, it's also the most common nutrient pollutant. And so this is an issue that we face as in agricultural industry or the agricultural enterprise. We are in this together. We have to understand there should be an optimization of nitrogen, not just simply a maximization of plant productivity. We see that all around the world, where there's industrialization of agriculture, we see these water bodies that are being affected. And so this is the eutrophic areas around the world are occurring. And so it is a problem. We need to fix this because it's our home. There's only one Earth. We shouldn't necessarily destroy it. We can do better, and we need to find ways to do that. So I wanted to bring some ideas to your attention. You know, this bothered me when I was growing up, is that, you only have to get big, otherwise, you'll be pushed out. Now, I'm glad that you all are here yet. But, and I saw some headline just recently, well, there are plenty, and what didn't come from a farmer, but it's basically the headline was, well, there are enough farmers, and there will be enough farmers. And that's maybe true. But it means that you're forced into a certain way of operation because you have to have hundreds of thousands of acres to be able to really make it. And the headlines are not just historical. They've occurred recently too. And so there's this squeeze. And I work for the USDA. But USDA is a very large department, and we have many agencies. And these are national level policies that are being developed. And for you, I don't want you to kick me out. I'm not sure if the gentleman is here, but I had to walk out and get my presentation. He asked, did they kick you out already? Well, no, they didn't kick me out yet. I hope you don't. But I think that there are a lot of things that many in USDA are working on that are a benefit to you. And that's where you need to take the chart. Okay, so we have a new chapter, and we shouldn't follow our nets because it's our home. We live in this environment. We have to be settled with this. And we can learn from our mistakes. It's difficult to be told that you're not doing it right. I have a difficult time at home, when my wife says, it should be this way and not that way. So, it's not easy. But, you need to sit down in the barn and think about it a little bit, and then maybe we'll come to our senses. Okay, and we need to build the future we want. I think that's what that was exciting to me to hear about this conference, Farming for the Future. Let's get the information that we have. Let's build our future, and we can do it the way we'd like to do it. And each individual farmer has that great capacity because you have this parcel of land, and you can do the things that you want to do. You can do it the way you want to do it. And there's opportunity for us to actually build a future together. And we really should be able to thrive, not just survive. We shouldn't just try to get by for this year and then that's it. We need to build our communities and we need to build our farms. Okay, so I'm gonna have to move a little bit quicker because I know I'm gonna run out of time. And so I wrote this article with some colleagues because I felt like the USDA leadership was leading us down a path with words that just didn't really resonate with me. And part of it was that the future of humanity and how agriculture can continue to support the food and fiber needs of a burgeoning population are threatened by agriculture's persistent negative effects on the environment. The idea was that the USDA Secretary of Agriculture was saying that we need to increase production by 50%. And I believe it was 50%, or maybe it was 30 to 50%. And then we need to reduce our effects on the environment. The focus has always been, in the past several decades, to increase production. Okay, we talk about reducing the negative environmental effects. But if we're only focused on increasing production, we don't really get to the second part of that equation. And that is the real problem that we face. We need to have a clear recognition that we need to have both. All right, the other parts of this abstract would be that essential natural resources that will be needed in increasingly greater capacity are being undermined by agricultural practices that continue to deplete the soil resource base, reduce habitat to support biodiversity, and emit harmful greenhouse gases that compromise our ability to withstand changes to the climate. And that last part about the climate change is really about reducing the amount of carbon back from the soil in the plant-soil continuum back into the atmosphere. And it's much better for y'all to have more organic matter near the surface of the soil than to have it in the atmosphere. There's no clear doubt about that. Solutions to these problems are available in known and increasingly well-documented approaches using agroecological principles that manage food production in harmony with nature, not against it. And this agroecology, this is a term that I wish that would be used more than regenerative agriculture, only because regenerative agriculture assumes that we're at such a low level that we have to regenerate our agriculture, that we have to build up. And there's nothing inherently wrong with the term, but I believe that it's something that Pope tries to posit one position against another. And I don't think that that's the way we need to do it. Agroecology has many options. It covers conservation agriculture. It covers regenerative agriculture. It covers organic farming and all sorts of other things. But it's part of that whole cycling that is necessary. This commentary provides a message that we should be seeking healing of our planet, not just less harm than in the past. It is an important distinction that needs to be considered for the future health of people and the planet. The idea here is that we need to be thinking towards the future and not just trying to overcome the dilemmas of the day.
All right. If the earth is the mother of all living things, then soil must be its womb, bearing richness beyond comprehension. Then too, carbon in soil should be considered the blood, energizing the entire body, enabling the earth to provide a multitude of ecosystem services. What we do on the land affects not only us, not only our pocketbook, not only our water quality, not the water quantity, but our neighbors in an indirect way, and people around the world in an indirect way. So what we need to do is be softer with our approach. Sometimes it's difficult for me to really understand this because when I traveled up here, I saw these oaks that were probably, 80 to 150 years old, lining some of the streets. Farm level streets. This reminded me of the place where I grew up in the eastern part of Nebraska. So that's my southern roots there. And then, of course, I moved farther south. But it's difficult. Your arms around that tree were humbling. That tree saw many things over its lifetime. And that requires human effort, at least in the past, or which requires a lot of diesel these days, to move these kinds of things and actually overcome the nature, because nature has a powerful way of dealing with our landscapes. So I just think that we could be a little softer in our approach, but I know that there are things that we should focus on to overcome the nature. So it really comes down to the basics, though. Soil, when you hold it in your hand, and I don't know how I'm going to do this. I was in a field in Kentucky. It had been in a pasture, and then it was no-tilled for a year. And I saw all of the earthworm castings and the rich nature of soil at the surface. And I have it in a bag here, and I don't know if I'll be able to pass it around. And maybe you don't really want me to pass it around because it's, some Kentucky farm soil. It's probably not something you want to see. But it just showed me how soil should be, how soil is being affected by the organisms in the soil, Not only the plant roots being the dominant one, the organism in the soil. That's what we really need to focus on. But it's all those other critters, the beetles and the earthworms and the enchytraeids. They're all important, but the basics are important. Soil health. It's basically, this long definition to focus on the function, and you can have a longer definition by the FAO. Maybe that's because it's an international body and they have to have longer definitions. But the basic premise here is the single word that they share, and that's function. Function of the soil is what's really important. Function of the soil is what you've relied on all of your careers in agriculture, and it's something that we want to avoid being malfunctioned. We don't want soil to be running off and actually losing the precious capability for it to produce plants. And it can produce plants for grain production, or it can produce plants for livestock production and human consumption afterwards. So the focus really should be on function. We want plants to produce food for our benefit. And the second thing is that we want it to supply water, nutrients, and plant growth promoting compounds. Those are the two fundamental aspects that most people in agriculture will be really concerned with. But there are many other functions that soil provides too. And that could be providing that physical stability, cycling nutrients, protecting water quality, storing carbon and nitrogen, enabling animal habitat, and then various other things related to biodiversity. All of these things are functions, and as scientists at universities, people are studying these things. They need to give you that information and provide you with that feedback. That's an important aspect. And I think that'll be, it'll be, once you have this background knowledge, along with the practical knowledge that you have on the farm, you can actually start seeing the connections that occur. And those connections can be really important. So why should we care? Well, soil is vitally important to many global issues, and they're listed here: food security, climate change, clean water. These are really important, high-level attributes that are important. Soil organic carbon powers many of those ecosystem services so that we can have these functions they're clearly present. And then conservation management is our vehicle that we can control. This management meaning human control. We can do something to our environment. And that's important. We can make choices. All right. I'm going to now dig into soil biological activity. I've studied this almost my whole scientific career. I went to school at Texas A&M, and I developed this idea that we should, how many are recent graduates, less than 10 years out of college? Okay, there are a few here. Yes? Anybody, did anybody get a master's degree, PhD? All right, very good. Okay, yes, older people too, absolutely. All right, I'm sorry, I didn't mean that old. I mean, old, you're more than 10 years out of college.
Yes,
right?
yes. About 30.
All right, okay. So what's fascinated me when I was down in hell, I said, you're not from Texas, so it's okay. It's really hot as hell down in Texas. It really is. You should appreciate being up. Okay, but when I was that 7 months of winter in Beaver Lodge was really difficult. I think 1 year was enough for me. Anyway, so the idea when I was in early graduate school and my PhD down in Texas, I had collected a lot of samples, and I was really interested in doing something and understanding organic matter and cycle. And then I started collecting hundreds and then thousands of samples, and I thought to myself, okay, they told me I have to keep them refrigerated until I get the analysis. I said, no, I can't do that. I just simply can't do that. So I went against the advice, and then I developed this test. And it's not necessarily new, because people had been doing this prior to the industrialization of agriculture. So prior to World War II, there were famous scientists. Selman Waksman was one who was promoting, I think he was at Rutgers University. He was promoting this idea of organic matter cycling and how nutrients were being supplied by simply allowing soil to do its thing. And so this is what I found here, is that when we dry a sample and then re-wet it, we get this burst of activity, and then eventually it's going to stabilize, where we could consider this more of a linear rate of response. And that can continue for weeks and weeks or months. But then, when we go longer and longer, all of our resources are being depleted because we've taken the soil out of its natural environment. We don't give it plants anymore to provide new carbon inputs. And so then we get depletion.
But the point here that I wanted to make is that we have this flush and this stabilization. You also see that the top layer, the 0 to 4 inches, is always higher than the deeper in the profile. And that's a natural consequence. That's the way soils in most of the temperate region of the world will act. They'll act like this way in the tropical regions too. But there are some cases where maybe there might be higher mineralization deeper in the profile. But in very few cases, 95% of the soils will act like this if we allow them to. Okay, so we have this flush and this basal respiration. And simply, we do this with a canning jar. You probably all have some canning jars laying around somewhere, and those canning jars can be put to good use. Of course, I learned all this from my grandmother and my mother who were canning, and they had plenty of jars. I didn't use their jars. I was down in Texas. They were in Nebraska. No problem. But the reason that I did this was that it's a simple vessel that can be sealed. And what we do is we put some soil in here. Let's see if I have some animations here. No, we have 2 bottles of soil here, little small glass bottles here, one on this side, one on that side. And in the middle, we have some sodium hydroxide. This is an alkali that actually absorbs the carbon dioxide that's emitted from the soil. So the soil is respiring, just like we are respiring in this room. If this room were sealed in a plastic wrap, and then we had a vessel of sodium hydroxide here, I'd be able to calculate after, say, this session today, how many people were in this room, because there would be a known amount of carbon dioxide that you all are emitting because of just nature. You know, we breathe, we respire carbon dioxide. That's what soil microorganisms do too. And so then by at the end of the day, we'd know how many people were in the room. If there were only me in here, there would be far less carbon dioxide than with all you in here. So that's how we quantify, well, what's happening in the soil? How many microorganisms are actually present, and what are they doing in the soil? Some of the organisms are, let's see, no one's seems to be sleeping yet. So that's good. So nobody's really resting, but that's what soil microorganisms do. So if I were giving this talk after lunch, you'd have plenty of them that of y'all that are sleeping, but I'd have to be speaking, right? So some of them are active, and some are sleeping, and some are, attentively listening. So that's the way it is in the soil microbial community too. They are doing things at different levels. And so what we're doing with this respiration is simply measuring the total in the room. All right, let's see. So this is the flush of activity. And we measure this as carbon mineralization. That's the term that I'll be using. And these details aren't really that necessary for you to understand, but some of them are that we need to get a representative sample. We need to know the soil depth, because actually the depth really matters. We need to dry the sample, sieve the sample, re-wet it, incubate it at optimal temperatures that would be equating to 77 degrees Fahrenheit, and then we need to trap the CO2. So this is all the simple procedure, but of course, every step in science has to have a documented protocol. And so it's important to know what those things are. And there have been other protocols that have been developed. The Cornell Soil Health Assessment is developed, and it uses a similar technique over here. There are some variations. Rick Haney, my colleague at Texas A&M at the time, he also was working with me on the development of that, and he developed his own test. And then Solvita adopted that to use with this color paddle, and basically use a jar, different type of jar with the soil in it, and absorb the CO2. So all of those things are one and the same. The details are actually important, but they're different among all those different tests. And this graphic here just basically shows you all the difference. So this is my lab here at NC State University. Haney Soil Health Test, Solvita Woods End, and the Cornell Cache. And you see that there are various differences in the soil processing, soil weight, water, incubation, CO2 detection. That may not be very important for you, but it's just pointing out that there are some differences. Like if I go back here, I tend to use coarsely sieved soil. And as a soil scientist, we've all been taught that you need to use 2 millimeters as a sieve size. It's too small for me. I don't believe in it. And so I've adopted 4.75 because we want to understand soil aggregation as well. The other thing is that I try to use a little bit more soil than the other tests. And then I'm using 50% water-filled pore space. And that's the reason that it's important is that just like you need water and you need air. Soil microorganisms need water, good balance of water and air. If they have too much water, then just like the fields that are ponded right now, they're saturated, and their biological activity is not optimized. And so we want to optimize that. All right, so those were just some details.
All right, let's get back to this curve, because this curve is really important to understand. And I'm going to show you some examples of why this curve is really important to understand. So available nitrogen, how do we actually determine this? We're going to determine the inorganic nitrogen in the surface soil, and we can do it deep in the profile. And we want to also characterize organic nitrogen, because when you think about it, inorganic nitrogen is probably likely 5% of the total nitrogen, up to 5% in the whole soil. Whereas organic nitrogen is the vast majority of it. So if I only took, like, say, that table over there and said, that's what we should know about when all of you are in the rest of the room, it wouldn't be really quite fair. It might be representative. Are you representative? No. Okay, you're not. Okay, I don't know. We can talk about it later. Okay, so the idea is that when we have low available nitrogen, now that available nitrogen is in the soil, and we could also think about it as no nitrogen fertilizer input, right? We could also think it that way. And if we have nitrogen input, if we increase the available nitrogen, we should get greater profit. That's what you've been told all along, is that you have low available nitrogen. We don't even have to measure it. So when you send in your sample, I don't know for sure. I don't know what does Michigan State have a soil testing lab?
Yes.
They do.
Now they send it out to another lab.
A commercial lab.
Yes.
Yeah. Right. Okay. I'm not trying to pick on anybody, but it's the same all around the country. That state labs simply, and even commercial labs, they typically don't measure inorganic nitrogen because they
tell you what crop are you growing and what yield do you want to get. Here's how many pounds of nitrogen.
There you go. All right.
We do have a pre-side dress test, though.
Yeah, that's there. You're requesting the inorganic nitrogen
at a time when
exactly.
It's available.
Absolutely, and labs can determine the inorganic nitrogen. It's very possible, but as a routine, they're not doing it because it's somewhat variable and it's very low, and it wouldn't really tell you how much nitrogen to apply to your crop because it's such a low amount. Okay, but if you apply nitrogen fertilizer, you're going to increase profitability. There's no doubt about it when available nitrogen is low. And that's what they're all assuming, is that we've done testing on highly responsive soils, and we apply fertilizer, we get this big yield increase, and it pays for the nitrogen fertilizer, and it gives you more profit. That's a good thing. There's nothing wrong with that. There's absolutely nothing wrong with it. However, there are sites with high nitrogen availability and low fertilizer response. And what we're doing when we simply use a blanket approach is fertilize the environment. Our environment just doesn't need to be fertilized. Invasive weeds and things like that, they're coming partly because of availability of nutrients, nitrogen, phosphorus. So we don't want to have that. It's not good for us either as humans. So the idea should be that we should increase the available nitrogen pool somehow. And we typically have done that through inorganic fertilizers, but we should know about these other things. And we want to increase it, but when we keep it in the organic form, then all of a sudden we are limiting the susceptibility of it for loss to the environment. Doesn't mean that it can't be lost from the environment, but it's tied up first, and then it's slowly released to the plant as the plant really kind of needs it. Now, it's very complicated, don't get me wrong. There's no simple solution, because all of these things, the release by the microorganisms requires appropriate temperature, moisture, and position in the soil profile. So that's all important to know, and it's difficult to actually estimate. Okay, so the research that I've done is focused on biologically active and also to characterize surface soil or inorganic nitrogen. So not all fields have the same available nitrogen. I'm going to give you some examples here. In this case here, we can get about 20% of the yield, relative yield, equating to approximately 56 pounds of nitrogen that could be from any of these sources here. Now in this case here, when I put the line here, I'm assuming that there's no inorganic fertilizer applied in this condition. That we're relying on this 56 is coming from somewhere in the inorganic and organic fertilizer. And this yield response would be quite good. We're still at this point where we're getting a large yield increase, and then it's stabilizing sometime thereafter. But that yield response is robust, but it shows that there's nitrogen that is available. And then we have also curves where we did a test on your farms or on a research station, and we get a less robust increase that's occurring with the first increments of nitrogen. That means that there's more nitrogen in the soil, and it's coming from these sources here, but it's typically more than the previous example.
We can also get yield responses that look like this, where we apply nitrogen and it's like, well, it sort of increased yield, but it didn't really increase yield. And then when we make the actual economic calculation, it probably didn't, help us at all. And that means that there was a lot of nitrogen in the soil and it came from these sources, but if we didn't measure it, we didn't know where it came from. And the idea is that we could start measuring it if we had enough resources to be able to do that. So the idea is that, well, okay, if you have enough money to pay for the soil analysis, then we could start getting at that. But we need some background testing that has to occur. All right. So what do these associations tell us? Not nitrogen mineralization. So that's, if we go back to here, let's just assume that a lot of this is coming from the biologically active nitrogen, because we can also measure the inorganic nitrogen, but typically it's very low. But so a lot of it, this biologically active would be considered equal to net nitrogen mineralization. Net nitrogen mineralization is transformation of organic matter into inorganic nitrogen. It's mediated by an organism in the soil, typically a bacteria or fungi that decomposes the organic matter and then essentially poops out nitrogen. That's kind of the basics of the process. And that's nature. That's the way things are. Nitrogen is mineralized continually. All right, so nitrogen mineralization is what we measure, and I measured it in 24 days is because we have optimum temperature and moisture, and in the field, it's not optimum temperature and moisture. That's the kicker here is that we can't really do this in a very quantitative manner because we don't know exactly what's on your field. We don't know what the conditions will be in the future, the next 3 or 4 weeks. So this optimization is important. The 24 days represents a growing season out in the field because temperature and moisture are suboptimal typically in the field compared to in the laboratory. But we measured as 24 days, and we can see that biological activity closely corresponds to net nitrogen mineralization. And this R squared equals 0.87. That means that 87% of the nitrogen mineralization could be predicted just from knowing the soil test biological activity. The issue is that this test here, well, I can get you in about 3 months, and this one I can get you within a week. So which one would you choose? One is measuring the real thing, although it's not really in your field, but the other one is associated. It's the activity of the organisms which we know will lead to nitrogen mineralization. That's the idea here. And we can use this because then all of a sudden this level of biological activity translates to 55 pounds of nitrogen per acre. And this level of biological activity translates to double that amount of nitrogen. So all of a sudden you could have fields on your farm that are different in biological activity, and you would not have to fertilize them all the same. You could have portions of your field that could be different in biological activity, and you wouldn't have to fertilize them all the same. That's getting down to the real detailed nature of your farm operation. But that's also, by doing that, if you can actually build biological activity, it won't last forever. You have to keep working at it, granted, but it's something for the future. It's not necessarily only for this year, it's for the future. You're going to draw that down slowly. It's like
soil type has an effect on this. Sandy versus heavy or organic must.
It could, yes, sir. But I'm going to try to tell you that it might not. So the idea here now that it depends on what we're actually trying to answer in that question. In this case here, that linear relationship is the relationship between nitrogen mineralization and biological activity. All right. Nitrogen mineralization. Okay, so why not just use organic carbon or total organic matter? People have proposed this to me. It's like, well, we have tests of organic matter already. Why don't we just use that and actually predict nitrogen mineralization? And we might be able to do that. The data in this example from some fields in North Carolina would suggest that there's a positive association. The association is relatively small. Only 22% of it is predicted by total organic carbon. So there's a possibility of doing it, but it's not really very fruitful, I think. Okay, but if you know that I took the samples in this case here from the coastal plain, which is along the Atlantic Ocean, the Piedmont, which is kind of at the foot of the mountain of the Appalachians, and then the Blue Ridge in the Appalachian region itself. And we see that there are different associations. So in North Carolina, people, I've presented this, and they say, well, we could have different associations in different regions, and that's fine. But then when you're in one county and you're bordering one region versus another, how do you separate? All of those things could be complicated, but I think the bigger issue is that where
So the idea here is that at a certain level of organic carbon, you have very different nitrogen mineralization that could occur in those regions. Or if you had searching for 100 units of nitrogen, you would have to achieve it with different levels of organic carbon. All right. Here's the idea that actually, if we substituted organic matter with the biologically active portion of soil, we'd actually see no difference among these regions. We'd be able to use one association and one association only. All right, this is getting to your question here now with the amount of clay and sand in the soil. So we did this nitrogen mineralization versus biological activity. This does not mean that clay soil, or in this case here, a sandy soil, less than 20% clay. This would be considered a sandy soil. This sandy soil has a lower potential, let's say, I think. That would be true. But the association between biological activity and nitrogen mineralization, that's what I'm focusing on here. That would suggest that there actually is no difference whether we had high clay or low clay. There would be the same association. That doesn't mean that let's see. Well, in this example, all of them they all approached, and this was just random sampling from sites around North Carolina and Virginia. And but typically we will see lower levels under sandier soils than under clay soils. It's a true fact. All right. Right, and so we can get the same association that I showed you before. Okay, I'm going to get to you. Now, I took these ideas in the laboratory. Okay, this all worked out. Let's recap here. The organic matter is important. The fraction of organic matter, the biologically active portion, is, for nutrient cycling, much more important to know. So what we're trying to do is get at the nitrogen supplying capacity of soil so that when you want a recommendation as to how much nitrogen, should you apply 1.2 pounds of nitrogen to a corn grain crop, or should you apply 0.8? So, this would be reducing it by a third, right, of the nitrogen. That would be a big difference, because when the fertilizer prices were at its peak, that would save you money. Because any amount of nitrogen that doesn't lead to profitability is loss. It's lost to your pocketbook. It's lost to the environment, and those are two things that we don't want to have. So I decided, okay, we need to take this to the field. We need to find farmers that are implementing various conservation approaches. Because if I only did this on poor ground that's been beat to death, where there's no nitrogen supplying capacity, what do you think I would find? I would find applying nitrogen fertilizer, I'd see this large increase, and then I'd see the plateau with varying nitrogen rates. Would that help y'all? To me, I thought, well, that's not going to help you, because it's just doing the same kind of thing that was done in the past. But we know that conservation approach, where we're leaving the soil undisturbed, building organic matter near the surface with cover crops, good crop rotation, using animal manures in the system appropriately, that leads to higher biological activity. And the end result, this is a little bit complicated to understand, but this is the inverse, and I'm going to have a graphic to illustrate that, but this is the inverse of the yield response. So values at the high end mean that there's this steep curve of nitrogen, of yield response to nitrogen. You need to apply nitrogen at that point. These high levels, you apply nitrogen fertilizer, you're getting profitability, absolutely. But when you start seeing sites that have high biological activity and they have very low, basically no yield response to the nitrogen fertilizer application, there's no economic benefit. And these data are from the soil test analysis of biological activity and in-field measurements, uncontrolled weather environments, different soil types within a region, and it shows that the relationship holds. We need to fertilize these parts of the field that are low biological activity, and we probably don't need to fertilize those parts or those fields that have high biological activity. These data were very compelling. Okay, this initial rate of yield gain per pound of nitrogen. That's this red line here. This is the slope, the instantaneous slope that occurs at the 0 pound of nitrogen. And it just shows that these were real field studies. I don't remember which study this was, but you see the data points. They're scattered around here. The yields are somewhat scattered there. And there, I'm just showing you that we had 3 different examples. One was 70 pounds of nitrogen, pounds of grain per pound of nitrogen, another 22 pounds of grain per pound of nitrogen, and the third one, 7 pounds of grain per pound of nitrogen. If
if a farmer were to apply, say, 100 units of nitrogen to each of those three examples, there'd be 2 of them that would be yielding probably economic profitability, and 1 of them that wouldn't, and that one would be right here, because there's just simply not enough yield response. And these data are shown again, and then basically the inverse. So this is the yield response. The first 50 pounds of nitrogen led to a large increase of yield. The first 50 pounds in this example here, in the middle point here, were leading to moderate levels of yield response. And then here at the far right end, very low yield response. And then, so that was all useful. But as a scientist, we call it research because we're never happy. We search and then we research it. And so it's something that we need to do because the world is complicated. It's possible that some things got in the way of my interpretation of why we got the results we got. And this is not any fault of anybody that does research. I wouldn't criticize research. I do criticize research. We need to be critical in our evaluation of research. But it's something that we need to, if we're not convinced, then let's just repeat. That's the way we solve that. So we repeated at different locations. These are the number of trials that occurred in different years here, all across this region. And what I wanted to tell you here is that I started characterizing because we had 158 sites, and this was the distribution of biological activity. So I characterized them into very low, medium, high, and very high categories. And you can see that the low and the medium are where most of the farm fields fell as far as biological activity. I'm going to show this to you because I'm now using those 5 categories, very low, medium, high, and very high. And that's characterizing the biological activity as a function of relative yield, the fraction of maximum yield. So this could be like, if you didn't fertilize the field, what would be the yield that would be out there? Of course, this is simply a fraction. The top is, you determine what it is. I don't know what your yields would be on a particular field. It could be 250 bushel an acre. It could be 125 bushel an acre. It might be 400 pounds per bushel an acre. And I don't know, that's independent, but these data would then be scalable. Okay, so there's this typical yield response curve that is logical. And then this grain yield response, as I showed in the other data, that it's an inverse situation. It's declining with biological activity. So all of a sudden we can see that we could actually change the way we have nitrogen fertilizer recommendations based on the biological activity. Now, there's nothing necessarily magical about using the test of the way that I use it. There could be other indicators that tell you about the biological activity. What we're trying to do is just simply use a test that tells us, is there nitrogen supplying capacity of the soil? That's what we want to do, but we want to be able to quantify it in a very logical manner so that when we do it repeatedly over time, we get the same result. And that's what I'm trying to do here. So in this case here, these levels of fertilizer, let's see, I think I have, yes. So this is the nitrogen factor for economically optimum production. So we oftentimes use 1.2 pounds of nitrogen per bushel of grain. You could use one. One was developed by Dr. George Stanford because he knew that the mass audience needed a simple approach. They needed to know, okay, we measure yield in bushels. Let's give them the amount of nitrogen in pounds of nitrogen per bushel. That's simply the way he actually did it. That was 50 years ago. And so we could use a value of 1. It would be close to it. And that is what most state recommendations would use, is that we're using this high level and saying that everybody should just do this. But when you do something different and you're trying to actually improve your soil using a conservation approach, then you could actually start seeing that you could maybe get down to 0.6. I think that if you could get down to 0.6 pounds of nitrogen per bushel, you are so much on the right track that's where you could stay for a long period of time. It's possible to have these very low levels, but that's only because there's massive amounts of, well, not massive, but there's a large amount of manure that's being applied to the soil. And so it's possible to reduce it further, but I don't think that that's where we need to necessarily get to. Now, if you're an organic farmer, that's where you want to see it, because actually you need to utilize all of the resources on your farm to utilize that nitrogen. And that's one way we can do it. But this indicator is what's important here. All right.
And doing that over time, though, depending on soil conditions, that really deplete your soils then more on nitrogen, or is this sustaining if you are able to somehow continue to get organic matter on that soil in some way or other? Because my concern is, that's what we did what we had commercial fertilizer. We farmed the hell out of this ground. We didn't have any fertilizer on. All of a sudden, then it wouldn't grow anything. So that's why we put commercial fertilizer on, because we depleted everything.
Sure. Good. Great question. Thank you for that. And if anybody else has questions, I don't need to finish my. The question was that will that be sustained over time? In that, so you were using inorganic fertilizer, and then you stop using it, and then you just don't see a yield response anymore. And that would be true, because essentially, from what I took at least, your question was related that I'm just making a change, just being blind. I don't have any backing evidence. The backing evidence is that we need to have some indicator that our soils are at a capability of providing nitrogen. And that would be the point that I'm trying to make here. There will be some decline. If you do nothing different and you start depleting soil, yes, of course, you're going to need the external nitrogen fertilizer. Absolutely. But the process of getting to high biological activity meant that you did something that you need to continue doing. Okay, and that is the nature of the world. Carbon cycling, nitrogen cycling is based on continuous cycling. It's not, we've grown in our society to only input-based operations, when in fact, the world works in a circle. In that, so we capture carbon dioxide from the atmosphere, it goes into the plant, it goes into the soil, the microorganisms feed on it, and they release it back to the atmosphere. And that cycle needs to continue. That's true. Nitrogen is captured from the atmosphere, and that would be captured through symbiotic organisms that actually can fix nitrogen. But of course, you can, all of the plants absorb nitrogen, and then that's how we can actually reutilize it in different places, right? Because our industrialization has many different aspects to it where we could start pooling resources from other places and utilize it on our farms. That means that you're depleting it from some other place. So that, we have to think about that. That's right. But there's excess nitrogen in our environment right now. So we could have ways to capture more nitrogen, certainly. And we need to, because it's energy intensive. It's contributing to the climate change in that producing nitrogen fertilizer produces CO2 because we're burning fossil fuels to ignite the process. All right. So, yes, ma'am.
So using your paper, could I just take one measurement of soil biological activity once a year? I don't know if you took them always at the same time, and then use that to basically calculate how much nitrogen to add and modify it year by year based on that. That's an equation, right? You're just plugging what you get, and you know how many pounds of nitrogen is required per acre to hit the optimal point.
That's correct. I'm going to repeat the question, perhaps for the recording. Is that you're asking have an equation developed so that actually a nitrogen fertilizer recommendation could be used if you take a sample periodically. That is definitely appropriate. Currently, what I do is in a research lab. All of the commercial labs are somewhat resistant for some reason. Maybe it's because of my 13 letters in my family name. And my mother had 13 letters in her family name too, and I'm glad she didn't hyphenate. But anyway, the commercial labs are really bent on that. They were proposed with a much shorter period of time of 1 day to make the analysis, and they don't want to go back. So they're stuck with that. They need to make a calibration. They have to make a calibration for these field observations. That's the important part. You could do that in a state, Michigan, or you could do it in a district. All of that could be done if people wanted to. It takes participation by active farmers, though, too, because we need to have in-field validation of this. The research is there, but it needs to be validated in different environments. I believe that it'll work in most environments in the United States, but you'll have to test that out. So that can be done.
The only equipment you need is a pH probe and a titration.
You need to get it. So I had those list of criteria. You need to get a good sample, but so the idea is that it's a burette to dispense alkali. You don't have to do a titration. You can use an infrared gas analyzer. It would probably be more appropriate and better quality. I'm just stuck in my old ways. I can do some new things and some not.
So I would say that it's a relatively simple thing. A commercial entrepreneur could start a business and do this biological testing. I'm going to just propose that it could be started up for, easily with let's say $100,000, and that's just a rough figure. Only because you need to have some space, you need to have a person devoted to it, and of course that person would be paid then from the revenue from your testing. So all of that, but in general, the cost of the test itself is $5 or less. And there are others that are charging more, but that I understand. They have space that they have to pay for. I have a research lab already paid for by the federal government, so thank you. 5 minutes, yeah. Okay, well, yeah. We can, I'm going to present this here because this is probably what you're more interested in. Well, what are the things that I can do to change biological activity? And really, you need to follow the 4 cell health principles by NRCS. That is really important. It doesn't mean that it's a menu or a prescription. You need to understand that you try to disturb soil less. It's important because when we disturb soil, it's like mixing the soup and you get it uniform. When in fact you want only a portion of that soup because that's the tastier part, So it's important to preserve, some things. And preserving microorganisms in soil can be a really good thing because when you see soil that is well developed from microbial activity, you understand we should not disturb it because it won't happen without lack of disturbance. So disturbance is really an important part. We need to maximize soil cover. We need to maximize biodiversity. That's plant diversity. Maybe it's integration of different operations on the farm. It's certainly with animals on there as well. And we need to really have continuous living roots. Now, I know that I'm not from Michigan. It's actually my first time on the ground in Michigan other than in the Detroit airport. So I have no clue. But when I drove up here, the fields, they looked like they were from Indiana maybe. Well, we're close to Indiana, right? And when I was coming from Kentucky into Indiana, it's like, well, okay, they're larger fields, but basically it's the same kind of stuff. Agriculture is agriculture. If you grow row crops, you're doing kind of the same thing. And if you're growing beef, they need grass. They need sometimes a barn. They need good fencing. They need tender, loving care. So all these things are similar around the country and around the world. So these principles work. It's not a prescription, but you need to think how you can use these principles more in your operation. All right. In this, I'm going to give you a few examples within the 3 minutes that I have left. And we sampled different farms under conventional tillage and no tillage. And of course, it's biased. I had more fields under no tillage in this operation, but that's the way I wanted. In fact, I wanted it biased. That was what I was looking for. Biological activity was statistically greater with no tillage than with conventional tillage. This is in the top 4 inches.
When you say no till, are you talking about when you do burn down?
Yes. Yes, it's crop land that's traditionally no-till. This was in Virginia and North Carolina. The traditional row crops of corn. There was obviously soybean in the rotation. There was cotton in the rotation in North Carolina, and I don't think we ever had any peanuts. Cover crops were involved too, but that's going to be my next slide. Okay. All right, nitrogen mineralization was greater with no tillage than with conventional tillage in the top 4 inches. That doesn't mean what happened below, okay? And then corn grain yield. Now this is just the average with the optimized nitrogen. The grain yield was statistically higher under no tillage than conventional tillage. But, this is, there's probably some bias in my results, right? I mean, I intentionally had larger numbers here. So I was going to producers that knew what they were doing, right? They had, but that would be the point also, that in research, we all sometimes don't know what we're doing, and then we try to compare 2 different things. I'm not knocking research because I am a researcher, but, reality is reality. That's why I've shifted more of my focus to sampling on farm, because you all know what you're doing. Well, maybe sometimes not. Okay. I understand. It's a difficult world. The key point is that if we use the nitrogen based on to achieve this yield,
we could actually save $19 per acre if we used the nitrogen recommendation because we had built up the nitrogen mineralization and accounted for it. So we could have $19 more per acre, whereas the conventional system, accounting for the nitrogen that was there, we could actually save some money too. And there's an asterisk here because it's actually statistically different than zero. So it was an improvement. The second example is with inorganic or organic and no organic amendment. And you can see that most of the farms had no organic amendment. Same kind of things that I have here. I'll just put them all up here, showing that there was opportunity for economic return. We saw that the nitrogen mineralization was greater with organic than without an organic amendment. And that was important, but there was no real yield difference. And then the effect of cover cropping. For the question that occurred, we had no cover crop, single species cover crop, and multi-species cover crop. And the biological activity kind of changed from left to right. It increased from left to right. Nitrogen mineralization increased from left to right. And grain yield was tended to be lower with the no cover and then greater with the cover cropping. And we can see that economically there was always a benefit to using this modified approach for nitrogen fertilizer recommendation, meaning that there's value even when there's no real large increase in biological activity compared to others. Of course, the 189 is certainly a good number yet, but it's not very high. Okay, so the idea, and just to wrap it up, is simply to say that we can actually change our soil organic matter quantity. Now, I didn't really show you much about total organic matter. I have a second section that I had some results with that, but actually the ideas are a little bit more in development. It's not about the total stock of organic matter that's in your soil. You may measure it. If I go into get out my probe and I'd measure the organic matter down to 2 feet, and that's my current approach. I'm trying to measure organic matter in the top 4 inches, the 4 to 12 inches, and the 12 to 24 inches. I want to know the depth distribution. And let's just say that God gave some of you good soil and some not so good soil. And that's a fact. You bought the farm in the condition that it was. And if you just bought the farm, you have to say that because you had nothing to do with it. Now, whoever farmed it before had something to do with it. And that can have an impact. But if we think about it, when we grow plants, we can see roots that go deep. But the vast majority of the roots are in the top 12 inches. That's why we actually only even sample the top 6 inches to estimate what is available to the roots that are mostly in the top 12 inches. Of course, roots can go down to 2, 3, or 4 feet. It's not improbable. But the vast majority of the roots, almost 80 to 90% of the roots will be in the top 12 inches. If you don't believe me, dig a pit. And do it even in the woods. I suspect you'll find at least 80% of the roots in the top foot of soil. Yes, sir.
Why is it on your multi-species cover crop the return is more, but your yield is less?
That's because this was a post-fact. I was assuming that I knew what the yield was going to be and applied nitrogen to that yield. We don't know what the yield is going to be. You have to make an estimate of what you think the yield would be, and then you apply nitrogen. So all of these are based on the results as they came in.
So is your yield less because you didn't apply as much nitrogen because you thought there would be more nitrogen on your multi-species cover crop?
The yield is really this is a survey across these farms. So these farms varied in various ways, and we couldn't really control. I can't say that the farm using multi-species wasn't in these other categories either. So it's only a survey type of research that we're doing here. And so the yield is actually statistically, it's no different. We have variation in both of those estimates, but these two were greater than this one here. So it's a valid question, no doubt, but we were applying the nitrogen fertilizer to the yield that was achieved. Because we had multiple nitrogen fertilizer inputs, we could select which one was the most appropriate.
Thank you.
Yeah, thank you. Okay, so and I'll answer your question, but I just wanted to conclude because otherwise I won't find my conclusion. I told you that organic matter is important, but it's the biologically active portion that you, on a day-to-day basis, can use. The total organic matter is a separate factor, and that depth distribution that I was trying to describe, there's a way where we can separate what was there inherently over thousands of years of soil formation versus what you've managed. What you've managed, I believe, I'm assuming, is in the top 12 inches. And so with that curve, I'm making calculations to find out actually how much carbon management history has contributed to versus what was inherently different. So we might say that soils in, let's pick on Iowa, right? They're known for high organic matter soils. They can have high organic matter, but in Georgia, we don't have high organic matter soils. But that's because that's nature. Those are climatic conditions over thousands of years that have done that. But I'll just project that actually the conservation approach can have just as much impact in Georgia as it does in Iowa. We'll leave it at that, and then maybe we'll find out more later. But your question,
Can you just flip back to that slide with how to manage or how to increase biodiversity? It's a circle.
Okay, yeah.
Go back. Sorry.
Yeah.
There we go. Thank you. I just need to jot those down.
Oh, okay. All right. Well, they're on, I believe, in Barry's slide too, because he's going to be talking about soil health.
When you're saying maximizing soil coverage, are you talking about cover crops?
Yes.
Okay.
But it shouldn't be focused only on cropland. This can be done in a grassland situation too. Pasture-based livestock systems, you want to make sure that you have cover. In the wintertime, it's very possible to see ground that's not covered
So
in a pasture-based livestock system, right? Some fields.
good pasture management.
Absolutely. Yeah. Now, sacrifice lots are important, and they may be reasonable on most farms. But we have other approaches to actually increase the biological activity and ground cover in pasture-based systems too.
Thank you.
Thank you.
So, okay, well, no, I was just trying to say, it's not working. We can ask more questions, but it's hard to hear the questions, so I was going to, well, you keep it just in case. We have a couple more questions, 2 more questions if someone wants to ask a question. We gotta be brief though.
I was just gonna ask if your slides will be available after this, or is there a way to contact you if you want to learn more?
Yeah, you have a file, and you can share. You're free to share that.
I have the slides. Let me know.
Thank you.
Any other questions? Blew their mind. Thank you so much, Alan.